everyone, welcome back to our YouTube channel, Becoming a ROS Developer. I'm Desire, and today we've got Faiz, who has just completed the course Linux Basics, and he'll be giving us a presentation on that. So first of all, we'll begin by seeing his code base running on the real robot, and then we'll get into the details about how he did his project. So without further ado, I will now hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Faiz, just check your camera if you can for me.
What's that?
Your camera, your visuals.
My display camera?
Yeah.
Yeah, so that's connected through with my phone right now.
Alright, so let's go on. Okay, that's working now perfectly.
Okay, so I'm just gonna go ahead and run the code for the robot itself, and I'm gonna go ahead and talk a little bit about how exactly it works, right? So I'm just gonna go in. Yeah, okay, so change the connection sheet.
I think we lost your screen there.
Yeah, sorry.
Alright.
Okay, so what you're looking at right now is basically a simple obstacle avoidance code system, where I'm using the robot interface Python file for reference of the actual
Faiz,
robot function.
we cannot see your screen.
Oh, you can't see the screen?
Yeah. Can you try resharing and then we...
Yeah, sure.
Okay, it's back now, thanks.
So I think there's been a bit of a network disconnection.
Okay.
It's terminated. So I'm just gonna have to rerun it.
Okay. Let's see, can you maybe try disconnecting and reconnecting again? I think.
Yeah, that's because the Wi-Fi most likely. I'm just gonna restart it.
Okay, yeah. Yeah, okay, it's taking longer.
Yeah. Okay, I think that's good.
Okay, yep.
So here, I'm going to select
You don't have to launch the simulation because you're connecting to the real robot already, so there's no need to launch the simulation.
No, I just want to also show the visualization for it, but that's fine. I can just leave it as is.
Oh, okay, all right.
Yeah.
You could show that later, since you're connected to the robot already. We'd rather see it on the robot first, so.
Okay, I'll do that. It seems to terminate this for some reason.
Can you?
Sure why.
Do you have any gazebo window that's open? Let's see.
I can turn that off.
Yeah, can you close gazebo window and? Okay. Then, can you close that terminal and open a new terminal? Okay. Yeah, yeah. Open a new terminal altogether, so you don't have to source the simulation workspace.
I'll just do this.
I think you're supposed to go in the SRC folder there.
The what?
The SRC folder first.
Oh yeah, I forgot about that. Yeah. So I'm gonna run the virtual crash. Oh, what?
Okay, do ls to check if it's there first.
Oh wait, 1 second. I wrote forgot to write the pipe.
You can just check by listing the folder contents so you can see. Yeah.
Yeah, it's there.
Okay, good. Yeah.
Yes.
Terminated again.
Was working just fine.
Can you?
Had to reopen the project altogether.
Okay. Just hang on. So this is gonna disconnect us from the robot, and then we'd have to reconnect again. Maybe we'll get better luck this time. So.
Yeah.
Okay. So you can. How many minutes do you have to connect? Can you check? Okay. 4 minutes. Okay. Let's see the simulation first, and then we can see how it does on the real robot when we get to the time.
Yeah, sure, that works. So actually some issue wrong with the project itself.
The issue.
I'll just hit home.
Do you have another copy? Oh.
No, the thing is, it was running completely fine just like 5-10 minutes ago.
Okay.
I'm not sure what happened. I did some test runs just to make sure everything was working.
Yeah. Okay.
And it happened to work out pretty well.
All right. So yeah, maybe refreshing it might help.
Yeah, that probably would be the trick. We do have another one that's on.
Okay. Can you move it out of the corner first so we can see if it responds to us?
Yeah, I'll do that first.
All right. Why is it saying interface terminated? Okay.
I'm not sure why it's doing that. Never touched the robot interface code at all.
You have made no changes to this file, is it?
Nothing. I haven't touched anything.
All right.
As is.
Can you? Oh, you didn't start the simulation. Oh, okay. You have to start the simulation first. But you're connected to the real robot, so it's supposed to work there. So okay, what's going on?
Yeah.
Can you go to the terminal and do ROS2 topic list to just see what topics we've got?
Can you say that again?
ROS2 topic list. Okay, so we've got all those ones being published. Okay, that's fine. So we're connected. Can you run tail up, or maybe try using the gamepad to move the robot out of the corner? I just want to see if it moves first.
Can we run what?
The gamepad, right on the bottom right.
Yeah, I'll do that.
Yeah. Okay, it moves. Okay, that's good.
Can try running tele off itself 1 second after that.
Okay. This one works, so it should be okay.
Seems to work fine.
Alright, so
Working really well.
let's try again and see.
Seems to stick by the one, so I don't think it's getting issued out. So
This okay. Okay, all of them are green. Okay.
Now I think it's going to do the job.
All right.
Okay, yeah. So it is running.
All right, that's good. That's good.
So, right. Should I go ahead and explain now?
Yeah. Well, as it does what it does, yes, you can be explaining what it is doing and which part of the code it's executing, right? We'll get through the code when we're finished with the demonstration, but you can be explaining, yes.
Okay, perfect. So, well, the first step that I did was going ahead and initializing with the robot interface for it to go ahead and get methods and being able to communicate to the robot itself.
Yep.
The second code I ran was the naive obstacle avoider. And basically, what it's doing right now is it's taking in the inputs of the scan methods, which basically I'm assuming is using the LiDAR itself and the IMU data. And then based off of these get methods, it understands whether or not it's close to a certain obstacle. That could be a wall or an object around it.
Yes.
And the threshold, which has been set as 0.3, if it meets that criteria, it's going to stop and look for the next plausible area for it to move ahead towards. If it's free. If all areas themselves are blocked out, essentially it just sort of stops and stands still because there isn't any safe place for it to go ahead and carry on its patrolling. Now, the next piece of code that I have executed is the ./robotics_statistics.bash file. And basically the robot statistics file, what it does is it guesses the statistics about the position and the velocity and acceleration of the actual robot itself.
Okay.
So we get things like the odometer position of X, Y, and Z. We see the orientation, the roll, the pitch, the yaw. So roll and pitch shouldn't really be affected at all because you're basically going on a flat planar surface. So there shouldn't be any change in that. If anything, it should be only yaw because you're just moving on a single axis in turning point. Likewise, we have the IMU angular velocity and the IMU linear acceleration description as well. So there's that. Additionally, it's paired with a distance covered section, which basically tells us how much distance has been covered since the start of its journey.
Yes.
And that is purely incorporating only distance and not actual displacement.
Okay.
I did consider at one point to include a displacement covered section as well, but the only hitch I had with that was trying to figure out a system or a tree method that allows it to save coordinate positions every few seconds.
Yeah.
So it can then check whether it's closest to the previous coordinate or not. So that took a bit longer, and given my current knowledge in the topic itself, because I was doing Linux as basics or foundations for Linux for ROS2, I could not achieve that, but I did try an attempt towards it, which was a failure as well.
Yeah, that's good.
I did go ahead and try making a wall following code as well, but there were some errors in that, so I can show that code as well later on. But the idea for that was it's supposed to only use the front and the right scanning methods.
Okay, so you wanted to do it using a base script. Okay, that would have been nice. Yep.
Yeah.
Okay.
Where it just follows the right side of the walls only, and it sticks to that, and it doesn't really care about the left. So if there's anything on the left, it stops. But if there's a wall on the right, follow through with it wherever it's going. So yeah, that's basically the idea. Demonstration-wise, I think the code does demonstrate what the robot is doing and what it's supposed to do. So yeah, that's the robot doing what it's supposed to do in real life.
All right. So can you walk us through your code now? I think you've been explaining quite a lot, but yeah, let's get to see it and highlight some of the parts that you wanna emphasize.
Okay. So I'll just go ahead and pop the code now. Okay. So we can start with
Let's start with the obstacle avoider first. I think that's the one that, yeah.
Right, so for the obstacle avoider, basically, at the very start, we have just some call-out messages to go ahead and say it's running, and then press Control C to terminate. After this, we're setting up the initial velocities and angular velocities for the robot to actually be at a standstill.
Mm-hmm.
Then we go ahead and define our threshold, which in our case is 0.3. I set it for. This area wasn't particularly useful for me, so I just left it blank. You didn't really need to. But over here in the while do loop, where it's constantly in a true state loop where it's scanning the left side,
Mm-hmm.
the front left side, front right, and the right side. And the reason for it to do that is because if it's constantly scanning its environment, it gets updates as to what exactly is going around it. And because it is a closed loop in this situation, it can constantly update what it has to do next. And in that situation, what it does next is through here itself. This is a conditional statement section where basically we're comparing the given range with the threshold at every given point.
Mm-hmm.
So this is for the front left. We have the front as well. We have the front right. So as well as the right. So it's checking all these different sections on the if statements for it,
Mm-hmm.
and based on that, it carries out an action. So the action basis is over here itself. And the way it works is you have an if condition. It checks for all the different parameters, and in this case, it's using 3 simultaneous check systems.
Mm-hmm.
So the front left, front, and the front right. And if they're all 0, then it goes ahead and checks it again, and then it says so and so meters for the left, so and so meters for the right. However, if in an event any of those are not 0,
Mm-hmm.
and it's within the range of that given thing, or if it's -1 of it, then it turns left, because avoiding that area altogether, because this is checking for the right range, if that makes sense. Does that make sense?
Okay, all right. I think you should go over that again. So what is the L doing? Can you explain to me the...
I'm just trying to find a definition for it because I written the code not too long ago. So 1 second. I'll do it right now. I think it's supposed to take 1 off. Check. Because I'm really trying to remember what it was at the given point to do so.
All right. So okay, as you think about that, can you tell me how you found the values for the angular velocity? Like, how did you choose to...
Okay, so the angular velocity values were basically, because it's in radians, this is 180 degrees in radians if you convert it, and that's mainly the reason as to why I picked that particular value and hard-coded it. I did consider taking it as an input value where it scans the left, right, or front, and then it calculates that in degrees and then converts it live. But then I was worried if I did it wrong, it would break the code on a regular basis if I didn't do it right, because execution needs to be consistent every single time. So I didn't want any hitches in that, so I just decided to put in a hard code value, where 0.31416 is basically a conversion of 180 degrees in degrees from radians.
Okay. Okay. So you want
likewise
to
turning right. Yeah, and likewise turning right is a negative value of that.
All right. I see.
Yeah.
But then, okay. So you are saying set command velocity, right? That's like the speed. You're not setting how much it rotates. You're setting the speed at which it rotates, right? And
so this would be the angular for it. So it's gonna go off at 31416.
Right. That's what I'm saying. You are setting the angular velocity because the definition of your command says set command vel angular, right? So
yes.
Right. So you are specifying the speed to be the speed of rotation to be 180 degrees per, let's say, per second, or per whatever time unit you're using.
Yeah. So it's 1.5 seconds over here.
Okay. So that is the amount of time it has to rotate at that speed.
Yeah.
Oh, okay, all right.
Yeah. Fair. Right.
So okay, here's another question, right? So at that speed, right, and it rotates for 1 second, that um how many degrees is it going to cover? Right, if it rotates at 100.31 radians every second, and it rotates
Mhm.
for
I could
1.5
try.
seconds, what's the angular distance that it will cover?
I could try some quick math to do that, if that's okay.
Yeah, why I'm asking this, right, is
Okay.
you had to find a way of figuring this out, right? Because you are trying to govern
Yes.
how much your robot rotates when it encounters an obstacle, right? So I'm trying to find out from you, how did you get to the choice of using that angular rotation speed and the amount of time it has to rotate, right? So um,
So the amount of time initially I put it on at 0.5.
mm-hmm,
Then I decided to go to 1 just to I sort of eyeballed that particular thing,
mm-hmm.
and then I stopped at 1.5 when I felt comfortable enough about it. It just seemed right about it, and it made sense of the 180-degree parameter.
Did it
And
work well? So when you tried point 0.5, what made you change it to 1 and then to 1.5? That's what I'm trying to understand.
so when I did point 0.5, um, it turned. By no doubt, it did turn, but it wasn't as great of a turn to actually consider obstacle avoidance per se. It
Okay.
was more so just obstacle deterrence. So it was just like slightly turning away from it, not completely avoiding it.
Okay. Yes,
And then
that's.
when I went to 1,
Uh-huh.
yeah, when I went to 1, it was just right, but there was always that possibility of it messing up.
Not
So I put
enough.
in the point 0.5, and it eyeballing that just sort of made sense at the time.
Okay. Oh, yeah, that's what I was trying to get. Because when we see numbers like this in a script, right, they are like
Yeah,
magic numbers, right? So we want to know, how did you get to that magic number if there's no comment that
yeah.
specifies?
It was a bit of a trial and error situation,
True.
mainly because I didn't have the physical robot in front of me to see how it would work out in real life.
Mm-hmm.
Yes, I did have the video footage live feed
Mm-hmm.
for it. However, it just there's always that difference between having the robot in front of you versus seeing it remotely, because at the end of the day, even though it is live feed, it still feels like somewhat of a simulation.
Mm-hmm. Mm-hmm. Okay, I hear
Yeah.
you.
Mm.
All right.
And plus, you also have to take into account that there was significant lag. So even if I were to time it just
Y-
to see, even though that's like the worst way to set up parameters,
yeah, true.
I wouldn't be able to confirm it.
Okay, okay, okay.
So yeah.
All right, all right.
Um, yeah. Then, well, again, so all of these different methods over here
Uh-huh.
are all, sorry, not methods, all like else if statements over here
Uh-huh.
are basically just there for the turning, for the left, for the right, for moving forward, and
Uh-huh.
all those kind of conditions. Because you can't just have a singular if statement that goes and says, if you see an object on the right, then turn left. What are
Uh-huh.
you going to do if there's an object on the or what are you going to do if it's in the front left, and so on.
Okay.
So I've just basically modified different conditions, because you can see 0, 1, 0, 0, 1, 1, 1, 0, 1, sorry, 1, 0, 0.
Okay. So
Basically
testing every
changing each
possible
and every
combination.
yeah, every
Okay.
possible combination.
Right.
I could have put it under variables in a loop,
Mm-hmm.
where basically I have a singular condition with alt executions, which are basically like, for example, I could have this while do loop,
Mm-hmm.
and then put in one master if condition,
Mm-hmm.
and then rest some of these else conditions underneath it, with the final execution being possibilities of each of these. But
Okay.
that would
Okay.
just be very complicated and very nested in itself to track, to go backwards if you're trying to see where it leads back to.
Yeah.
So
True.
I
You
separated them
wanna.
all into individual ones,
I see.
and went ahead from there on.
Uh huh.
But yeah, so there's that. And then lastly, basically, I'm just sort of going ahead and printing out all these details here.
Okay.
Moving forward, meters forward, all these things. So yeah. And then there's just a divider to print lines between every single iteration.
All right. Thanks very much, Faiz. We are out of time, but job well done. Thank you for taking us through the details in as much information as possible, because we wanted to understand, right? How did you get those numbers? So thank you so much. And just have Alright everyone, this was Faiz's presentation, and warm congratulations to him. Would like to thank him for taking us through all those details and explaining